Hey guys, this is Mrs. Steele, and I'm here to go over one example problem of how to calculate the total heat required when you're heating water, for example. So step number one, grab your worksheet that's called Worksheet Heating Curve of Water. And if you look up at the top, you'll see an example of a typical heating curve for something like water. And it'll have kind of the zigzag design to it. And so step one, do you recognize what all of these parts are, like what's happening phase-wise? Notice that there are certain periods along this graph where the temperature is increasing. So you have one state of matter, for example, solid, and then like from C to D, you've got a liquid, and like from E to F, you've got the gas phase. And all it's doing is changing or rising in temperature. So all of the heat that's being absorbed is being used to cause an increase in temperature. In contrast, between steps B and C, as well as D to E, you'll notice that the temperature stays constant. At these points, we have what are called phase changes, okay? So the substance is changing phase, for example, from B to C, from solid to liquid. And from step D to E, the substance is changing phase from liquid to gas, okay? So you are responsible for being able to either interpret an already prepared heating curve or possibly create one of these given enough data. So a couple of important things you should know about water in particular. You should know that the freezing point of water is 0 degrees Celsius, and you should know that the boiling point of water is 100 degrees Celsius, okay? Therefore, these temperatures are already known, and you don't have to guess along this step or this step here, okay? So I think at this point, now that you understand the 5 main parts of a typical heating curve for a substance, I wanted to do example problem number 9 from your worksheet. So let your eyes fall down or drift down to the bottom of the page, and you'll see example number 9. It says that you have a 2-gram sample of water, and it's being heated from negative 20 degrees Celsius up to 120 degrees Celsius. So there are some particular some particular equations that you're going to need in order to help you with this problem. Those equations are provided in step or question 8. So if you look back at step 8 on your worksheet, you will see these 3 equations. The first one should look familiar to you from your previous chemistry experience. That is the heat equation, or Q equals MCAT, as some people say. Q stands for heat, M stands for mass, C stands for the specific heat capacity, and delta T is the change in temperature. That'd be the final temperature minus the initial temperature, in that order. Anytime you need to use this equation, you will notice, let me change color with my marker here. You're going to notice, let's highlight. There we go. You're going to see that the temperature is increasing. So for example, from step A to B, the temperature is changing. So it makes sense that we would use Q equals MC delta T. The same is true along step C to D. The temperature is increasing. So we would use Q equals MC delta T. We would also do the same at steps E through F. So I'm just going to highlight this equation so that it'll match the highlighted portions of the heating curve above, okay? So there's only one extra thing that you need to be sensitive to, and that is that some substances vary in specific heat capacity depending on what phase they're in. So for example, water in the solid phase has a unique specific heat capacity, or C, on your Q equals MC delta T equation. When it's a liquid, it has a whole different specific heat. And when it's a gas, it has an even different specific heat value. They all have the same unit, and the unit makes sense because if you look in your textbook and it says specific heat capacity is how much energy in joules it takes to increase the temperature of a 1 gram sample by 1 degree Celsius. So this unit is not some sort of weird, somebody just contrived it. It actually matches the definition of specific heat capacity. So it makes sense that all three of them would have the same unit because they are the same quantity. Now, two equations that you may not have experience with depending on your previous chemistry experience. You may not have come across these two, so I'll highlight them. This is the heat that's required for a phase change to occur. So do you see that the mass is still important, M, but you also may notice that it includes this new value, which we call enthalpy. And I have trouble remembering that one sometimes. So I think heat flow, like energy flow. So essentially what this is saying is that there's a certain amount of energy that is required to cause a phase change to occur, okay? So right here, vaporization is happening at step D to E, from point D to E. So I would use this equation in order to determine how much heat it would take for that certain mass sample to change phase from a liquid to a gas, okay? So, since we're weakening our intermolecular forces of attraction, you're going to notice that the amount of heat required is pretty big. I hope you guys notice that. It's in kilojoules, which is different from what our specific heat capacities on the left were in. They were in joules. We'll talk more about the units in just a second. But essentially, this is saying that in order for 1 mole of your sample to change phase, to go from a liquid to a gas, you need to apply 40.7 kilojoules of energy to your sample to make it weaken those intermolecular forces of attraction to the point that the molecules separate away from each other and are now converted to the gas phase. Finally, there's another equation here, so let me change colors one last time. Maybe this lavender looks good. Okay. When you look at steps B to C, this represents when the substance is changing phase from a solid to a liquid. So it would be appropriate for me to use Q equals M delta H. Notice the temperature is not changing, so I can't use Q equals MC delta T. Rather, I use Q equals M delta H for fusion because all of the energy is being used. It's being absorbed by the sample in order to weaken the lattice points that are holding the solid together, which will allow the molecules to more freely flow around each other, which is more typical of a liquid. So it takes a certain amount of energy in order to cause the phase to change from a solid to a liquid. And this is the value for the enthalpy of fusion, which you can find for water. I found these values online. I am confident that they are found in chapter 10, I believe, of the textbook. And they probably are also in the reference section, which we call the appendix, which is in the back of the textbook as well, okay? Now that we've been over the difference between these three Q equations that you see, the yellow, the green, and the purple here, now we need to do some heat calculations. So I'm actually going to walk through question 9 from start to finish. I'm going to describe to you which formula to use, and I'm going to show you how to set up the calculations. If you read question number 9, they want you to calculate how much heat is required for all 5 steps. Here, 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 here. So that means whatever I get for the individual answers, I'm going to add them together to get my total heat required for this entire process to occur. Here's my big reminder as your teacher. The most common issue that students have with this question is units. I have noticed that when students miss this question, it's not because they don't know what equation to use. Rather, it's that they have neglected to show their units and therefore are adding things together that don't have compatible units. Let me give you an example by working through the steps. So step 1, we're going to calculate the energy required from step A to B. So if you're following with me, we're looking from here to here, okay? A to B. So I noticed that the temperature is changing, so it would be appropriate for me to use Q equals MC delta T, as we already addressed. So the formula I'm going to use is Q equals MC delta T. However, I need to specify which specific heat I'm going to use. And I'm going to use solid specific heat capacity for water because it's in the solid phase. So now let's plug in the values. I know that the mass of my sample is 2 grams. That was provided in the word problem. I know the specific heat capacity for water when it's in the ice phase or the solid phase, so 2.10 joules per gram degree Celsius. And I also notice the temperature. So let's go back up. When you read the question from the text, let's see, I paraphrased it here. It said 2 grams of water are heated from -20 up to 120. But I'm only concerned about from here to here on my heating curve, from A to B. So that's from -20 to 0, -20 degrees Celsius to 0. The way you calculate change in temperature, you take final minus initial. So that'd be 0 minus -20. 2 negatives or minus a negative, that's a positive. So 0 minus -20 would be a change in temperature of 20 degrees Celsius, like so. Okay? So what we're going to do now is we're going to cancel out the units that can. So the grams cancel, the Celsius cancels, and we're left with joules, which is appropriate. And then you can do your math in your calculator, okay? So I'm just going to quickly grab a little handheld calculator here, and 2 times 2.1 times 20, and I'm getting 84, okay? I can double check that just to make sure. 2 times 2.1 times 20, yep, 84. So I double checked, that's my joules. Now, ideally, you would try to be sensitive to sig figs, but when this problem was designed, I don't think that the original designer of this assignment was really stressing about sig figs, so I'm not going to pressure you guys with sig figs right now, okay? So I'm just going to say 84. Let's move on. Step B to C, let's go up to the graph. Step B to C is the purple or lavender kind of color section right there, where we're undergoing a phase change. Notice how the temperature did not change. Therefore, Q equals MC delta T would be inappropriate. Can't use that equation. Rather, I need to use one of the Q equals M delta H, or mass times change in enthalpy. But specifically, I need the one for fusion because that's what's occurring when you are phase changing from solid to liquid or from liquid back to solid. Okay? So let's write that equation down. Q equals M delta H, and specifically for fusion. Now, the mass of the sample has not changed. I started with 2 grams, it's still 2 grams. However, the delta H is different. I got to use 6.02 kilojoules per mole. Does anybody see a problem here? I see a couple of problems. The first problem I see is that I have grams originally, and then somehow this particular value I found online, or you can find in the textbook, is in kilojoules per mole. Well, grams and moles don't cancel. So I need some value for water that can help me convert from grams to moles. Molar mass. And I just know, because we use water so much, the molar mass of water is 18.02 grams per mole. So I'm going to set that in this problem in such a way, I'm going to divide so that the grams cancel and the moles also cancel. So I just got the molar mass of water for anybody that's wondering there. The moles cancel like that, the grams cancel like that. Now I have an answer, or I can calculate my answer rather. Let's see. So in your calculator, 2 times 6.02 times, 2 times 6.02 divided by 18.02. So for this answer, I'm getting 0.668, or you could say 0.67 if that's bothering you. And if you look, the unit is kilojoules. Now you may look at this number and you go, whoa, this is really small compared to steps A to B. You'd be right. However, notice the units are not matching up. So I need to take my step A to B and maybe I need to convert that to kilojoules so that they're lined up, like they're the same kind of final answer. 0.084 kilojoules. There we go. Now I'm kind of comparing like units. So, it didn't take very much energy to make something increase in temperature when it's a solid, but it took a substantial bit more energy to cause it to phase change. And that would make sense because you're weakening attractions between the particles involved. So that's going to take more energy to weaken those attractions than it would be just to make the temperature go up a little bit. All right, let's move on. So for the next step, step C to D, that would be the yellow zone on our graph. And notice that the temperature is going all the way from 0 to 100. So I need to use Q equals MC delta T because the temperature is changing. The mass of the sample has not changed. It's still 2 grams. The specific heat, I need to slow down and think about what phase is present. When I'm from step C to D, I have a liquid phase present, and only liquid from step C to D. That liquid is just increasing in temperature, but it's not phase changing. So now I need to choose the specific heat capacity for water when it's in the liquid phase. So that's probably the one you're most familiar with, 4.18 joules per gram degree Celsius. Please show your units. It'll help you from making a calculation error. Finally, you have to calculate the delta T. You can either do it in your head, you can do it with your calculator, whatever. But I noticed the final temp was 100 right here, and the initial temp was 0. So from 100 minus 0, that's a difference of 100 degrees Celsius. Okay? Let the grams cancel, Celsius cancels. I'm going to get joules. Grab your calculator again. Let's do that. 2 times 4.18 times 100. And I'm getting 836. Be comfortable. Be confident in your work. If you know you've set everything up and the units are canceling, don't let that big number scare you. Keep in mind that the temperature increase during this liquid phase was drastically bigger, like a big change in temperature. Also, you may notice that the specific heat capacity for the liquid phase is actually higher than it was for the solid phase. So in other words, to make liquid water increase in temperature by 1 degree Celsius, it requires almost double the amount of joules as it would to do the same with ice. So this number is okay. I would change it to kilojoules just so it matches the units for the previous. So I'm getting this. And there we go. Let's move on. So for the next one, let's go from steps D to E. Step D to E is that green section there where we're changing from a liquid to a gas. So notice that the temperature is not changing. I can't use Q equals MC delta T. Rather, I am going to use Q equals M delta H of vaporization. I know this because I'm changing from a liquid to a gas. So that is the very definition of vaporizing something, right? Making a gas. At this point, you should almost be working on autopilot here, but we'll slow down and think about it. The mass of the sample is conserved. It stays the same the entire time. The change in enthalpy, hold on. Okay, the change in enthalpy of fusion should be for the vaporization, which is up here, 40.7 kilojoules per mole. So I'm going to put that in, 40.7 kilojoules per mole. And then your spidey sense should be tingling here like, ooh, these units aren't matching up. So how do we fix that? How do we resolve that? I'm going to divide by the molar mass, so that the grams cancel and so that the moles cancel. So I'm dividing by the molar mass of water since my sample is water. Moles cancel, grams cancel. Grab your calculator. 2 times 40.7 equals, divided by 18.02 equals, and I am getting 4.5, we'll say 2, just to be kind of lazy with our sig figs here. 4.52 kilojoules. All right. So an interesting observation I'm seeing here is it's taking even more energy to cause something to change phase from a liquid to a gas. That also makes sense, at least for water, because you are completely weakening those hydrogen bonding, those strong intermolecular forces of attraction between the water molecules. So it's going to take a ton of input of energy in order to cause those water molecules to break away from each other. Last step. Now we're at steps E through F. Your substance has completely vaporized. It's already a gas at that point, and the temperature just creeps up and up and up. So once again, I'm going to use the one where the temperature is changing. That's Q equals MC delta T. That's our yellow equation. Okay? So let's scroll on down. Whoop. Don't want to highlight all that. There we go. Okay, we don't want to highlight everything. Q equals MC delta T. The mass has been conserved. It means it stayed the same the whole time. So 2 grams. The specific heat this time is for when water is in the gaseous phase. So pay attention to that. We're going to use that 1.90 value that you guys see on your worksheet. 1.90 joules per gram times degrees Celsius, like that. And then we're going to multiply times the change in temp. If we look at the original problem, this substance went up to a temperature of 120, but keep in mind where you are. You started at step E, which is 100 degrees, and you went all the way up to 120. So if you get the difference there, that's a difference of 20 degrees Celsius. So 2 times 1.9 times 20, and I'm getting 76. 76 what? Oh, joules. So I'm going to need to change that over to kilojoules so that the units can match up with all the other ones that I've gotten. So when I convert that, I get 0.076 kilojoules. Side note for anybody that's wondering, like, I'm assuming that you guys understand kilo versus base unit, but for anybody that was a little confused how I just jumped from joules to kilojoules, I know that for every 1 kilojoule, it takes 1,000 joules. So I just divided my answer in joules by 1,000 in order to get it to kilojoules. So that's just for anybody that was wondering how I was kind of skipping that step. On the AP exam, you don't necessarily have to prove that. You could just convert it, like just hop the decimal over 3 hops to the left. So now I'm going to take those 5 answers that I've collected, 0.084 kilojoules plus 0.67 kilojoules plus 0.836 kilojoules plus 4.52 kilojoules plus 0.076 kilojoules, and I'm getting a final answer. So the total heat from steps A to F, all I did was just add them up, and I'm getting 6.186 kilojoules. If you wanted to put that in joules, you could. You could say 6.186 times 10 to the 3 joules. I'm going to double check my math because it's really easy with all this work to make an error. I'm just going to do 0.084 one more time. And yep, I'm getting the same answer twice, so hopefully I'm on the right track right there. So all I'm going to do, just to kind of finish all of this up, I'm just going to, oops, well, there we go. I'm just going to circle that answer there so you guys can see it better. From start to finish, this entire phase changing process took 6.186 kilojoules, which during this level of chemistry maybe doesn't mean that much for you. But if you start looking at other examples of this, not only in this unit, but in the next unit, which is thermochem, you'll start to realize the magnitude of this value and what it really means in comparison to other substances. Long story short, what's really interesting about water is that it has a very interesting property that because of its strong intermolecular forces of attraction, it can really absorb quite a bit of heat before it changes to the gaseous phase. So it has a really high heat of vaporization. So it takes a lot of energy for it to phase change to the gas phase. And another interesting observation is that since in the liquid phase, it has such a high specific heat capacity, that 4.18 value that you see there, it actually can absorb quite a bit of heat before it changes by 1 degree Celsius. So that's why we often refer to water as a coolant, because it can take or absorb heat that is generated by other substances and allow those other substances to stay cool while the water just absorbs all of it before it goes up in temperature. So that's kind of two cool properties of water that are expressed or shown to be true based on these calculations here. Anyway, this was a very extensive explanation, but I hope that me going through this question step by step will help you to feel more confident doing the following questions that are on the back of this assignment. I'm referring to the ones that say calculations involving phase changes, as well as the ones at the bottom underneath that say mixed thermochemistry problems. Please attempt those questions and come to class with any follow-up questions you may have for me. All right, hope this was helpful.